Hello everyone, Lucky here. We are constantly bathed in a shower of radiation, such as cosmic rays from distant supernovae, neutrinos from the thermonuclear fusion in the core of the sun, and particles ejected from naturally occurring radioactive materials. However, this radiation is invisible to us, with a few exceptions at very high intensities. It's always creeped me out that there are some materials that look like a regular rock or chunk of metal, but will blast apart your DNA with invisible rays if you spend too much time around them. Today, we're going to change that by making a device called a cloud chamber that makes these invisible rays visible. This video will cover the physics behind how they work and how you can build one yourself for under $100. Cloud chambers are simple but versatile devices for detecting radiation. Instead of just hearing a click from a Geiger counter to tell you when a particle was detected, cloud chambers actually show you the trail of the radiation, which can tell you where it came from, what type of radiation it is, and even properties like its charge, mass, and speed for more advanced cloud chambers. Radiation can refer to lots of different things, including the entire electromagnetic spectrum from radio waves up to gamma rays, as well as particles ejected during radioactive decay, and lots of exotic particles coming from cosmic ray collisions or particle colliders. Cloud chambers only detect ionizing radiation, which is any kind of radiation that can rip electrons off of nearby molecules as it travels through the air, leaving behind a trail of ions and electrons. This means we won't be able to detect low-energy radiation like radio waves or non-interacting particles like neutrinos, but most radioactive materials produce ionizing radiation that we can detect. These ion trails aren't visible to the naked eye, which is why we need a cloud chamber to see them. A typical cloud chamber is a sealed container with an alcohol-soaked sponge on top and a cold plate on the bottom. Alcohol evaporates off of the sponge and mixes with the air. As the alcohol diffuses downward, it encounters colder air, which can't hold as much alcohol vapor. This causes some of the vapor to condense into a cloud of liquid droplets. However, it takes a little bit of energy to start forming a droplet because surface tension resists the creation of a liquid-vapor interface on the droplet surface. It's a bit surprising to me that surface tension, which is essentially the force of a liquid sticking to itself, would resist the creation of a liquid droplet, but I won't get too deep into the physics here. The important thing is that it takes a bit of energy to start forming a droplet. Until something provides this energy, the vapor will stay supersaturated, where it stays as a vapor even though it would condense into a liquid if there was a nearby droplet that it could join. There's lots of neat experiments you can do with supersaturation, like cloud seeding or instantly freezing water. Let's take a look at what happens on the molecular scale when ionizing radiation passes through the supersaturated alcohol layer. The ionizing radiation leaves a trail of ions and electrons as it collides with the molecules in the atmosphere. These charged particles attract nearby alcohol molecules, overcoming the forces of surface tension and creating a microscopic droplet. Now that we have microscopic droplets available, they'll quickly grow into droplets that are big enough to see. This is the principle behind how a diffusion-type cloud chamber works. Another type of cloud chamber, called a Wilson chamber, lowers the pressure instead of lowering the temperature to create its supersaturated atmosphere. This can be a nice feature because the pressure is more uniform throughout the chamber than the temperature, which makes tracks visible throughout the whole volume of the chamber. However, I decided not to use this design because it requires moving parts, which I didn't want to deal with. We can improve the visibility of the ion trails by adding an electric field. The electric field helps separate the ions and electrons in the radiation trail, allowing them to have a greater chance of nucleating a droplet before they recombine. I found this to be very helpful for making the trails visible and better defined. The electric field also helps remove other contaminants like dust particles that can cause nucleation and gets rid of old ion trails faster. Now that we have the physics out of the way, let's see how we can actually build one. Be mindful of the hazards involved though, since this build involves cryogenic temperatures, high voltage, flammable liquids, and ionizing radiation. Here's a cloud chamber design that I find works well. I'm using a petri dish as the chamber itself. These felt pads that are super glued onto the top here hold the alcohol, and I put a piece of black paper on the bottom to act as a dark background so that it's easier to see the radiation trails. This all goes onto this heatsink here. This is a heatsink originally meant to cool a CPU. It's just something I had lying around, and this is immersed inside a bath of alcohol, and the alcohol is cooled by chunks of dry ice. This part isn't really necessary. You can also just put the chamber directly on a chunk of dry ice, but I'm using this way because I like that it doesn't shift around as the dry ice sublimates and changes shape. If you don't want to use dry ice, You can also cool the chamber using these Peltier coolers. These are pretty nice because they're purely electrical. The way they work is you apply a voltage to them, and they'll pump heat from one side to the other. So the cold side here is on top, and the hot side is on the bottom, which is connected to these heat sinks, and these would get immersed in a bath of ice water. These are nice because they don't require dry ice, but one of the downsides is they do use up a lot of power, and all that power gets converted to heat inside them, which also needs to be pumped out. So that means that it's really difficult to get them to even get close to dry ice temperatures. So that's why I stopped using them. It's very difficult, almost impossible, to see the radiation trails under just normal room lights. So I'm using this laser here with a glass rod taped to the front as my light source. This way it provides a nice thin line as the light source, so I can illuminate the radiation trails without bouncing too much light off the top and bottom of the chamber. Another thing that I found was really important to help see the trails clearly was applying high voltage. So that's what this ring here is. This is connected to the high voltage side of this flyback transformer here. This ring gets charged up to a few thousand volts relative to the heatsink underneath it. This helps make the radiation trails clearer. The flyback transformer is driven by a ZVS driver circuit, which is then in turn driven by this DC power supply here. There are other ways to do this. If you don't want to use a dedicated circuit, you can also just use a piece of PVC pipe and charge it up by rubbing it against a paper towel or something, and then just touching it to the top of the chamber. It visually looks about the same. The radiation trails are visible either way, but I went with this method because I didn't want to have to keep manually charging up the top of the chamber. You can see we're already starting to get some super cool vapor in there condensing, so it's already beginning to work. I also keep this jar of warm isopropyl alcohol here. This helps get rid of the fog and stuff on the surface of the chamber. I've also seen these little puffs here. As the gas inside cools down and contracts, it'll occasionally draw a bubble in from the outside, but these will disappear as the air cools down inside the chamber. All right, I'll just put my phone up here on this stand. Now I'll shut the lights off. And I will adjust the height of the laser so that we're getting just a little bit of alcohol condensation. So we're right near the edge. You can also see already there's a little bit of background radiation visible. Those lines dashing back and forth. Now I'll put a piece of radioactive strontium-90 on the top, and you can see we're already getting particle trails. Now when I apply the high voltage, the trails become a lot clearer. And I can also mess around with the light source position and height to highlight different trails. But this is generally how the cloud chamber works. In total, this build cost me around $90, including the high voltage supply, although I used a lot of materials I had lying around. Now let's see some neat experiments you can do with this cloud chamber. The most visibly interesting one is detecting alpha particles. This is a button of americium-241 that I took out of an ionization-type smoke detector. Americium gives off alpha particles when it decays, which are basically helium nuclei moving at high speed. The trails produced are thick and short because alpha particles interact strongly with the atmosphere, creating lots of ions and being neutralized after traveling just a couple millimeters. This low penetration power means the source is safe to pick up, even though it makes a Geiger counter go crazy. This is because almost all the alpha particles will be stopped by the dead outer layer of my skin. Here's a piece of uranium foil. Uranium and its decay products give off alpha and beta particles. Beta particles are high-energy electrons, which are much lighter than alpha particles. This causes them to make more curvy trails as they get pushed around by collisions with the atmosphere. Beta particles do not interact with the air as strongly as alpha particles, making their trails longer and more wispy. I also tried firing a beam of X-rays at the cloud chamber from an old veterinary X-ray machine. The X-rays themselves don't leave trails, but we can infer their existence by seeing the electrons they kick off of atoms. This is by far the most dangerous radiation source I used, so I only fired it for a fraction of a second while I was standing far away. Even at its lowest setting, the chamber is completely overloaded. I tried again with the X-ray machine placed 30 feet away from the chamber, and the beam aimed to the side of the chamber instead of directly at it. This time, only a few radiation trails are visible, probably from X-rays scattered off of other objects. Here are some containers of thorium oxide I've been keeping in an airtight bag. Thorium eventually decays into radon gas. I sucked up some of the gas from the bag in a syringe and injected it into the cloud chamber. Radon-220 decays into polonium-216, which then decays again after only about a tenth of a second. This is why the trails are V-shaped. The radon atom decays and then decays again before it's had a chance to move very far. Cloud chambers are just one of many ways of detecting ionizing radiation. Another way that's fun to mess around with is exposing camera film. Here's a piece of film I left with some radiation sources on top of it for a week in a darkroom. Another way is to just use a phone camera. Ionizing radiation can stimulate a pixel on the camera sensor, just like a photon of visible light. This is what causes cameras to go staticky when looking at intensely radioactive objects. Here's some long exposure photos I took from my phone, with radioactive objects pressed to the lens. And here's what it looks like in the path of an X-ray beam. I hope you found this video interesting. If you try to build a cloud chamber yourself and it doesn't work the first time, don't give up. It took me many failed designs before I finally got the conditions right to see radiation trails, which is why I wanted to make this video in the first place. Like and subscribe if you'd like to see more about radiation experiments and other topics. Next time, I'll hopefully be using this cloud chamber to detect antimatter. Thanks for watching!